Hello everyone, welcome to COMP359, Design and Analysis of Algorithms at University of Fraser Valley. In this video, we are going to talk about network flow, the two problems of maximum flows and minimum cuts on networks. So let me actually just give you a little background about these two problems. In 1954, in fact, I don't exactly know the complete name, but Harris and Ross actually modeled the Soviet rail network. It was actually during the Cold War, I guess. And they, in fact, modeled the Soviet rail network in a form of 44 different regions, considered them as vertices, and the roads between these regions as edges, which was 105 different edges. In this graph, unlike the usual graphs that we consider the edges to be the distance, here the weight of each edge is in fact the rate of material that could be shifted between two different regions. If there is a edge between them that shows a road, the weight that we assign is in fact the rate at which material could be shipped on that road. And now the question is not something like minimum distance or finding a path here, but the problem is that they wanted to find the maximum amount of stuffs that it can be shipped from Russia to Europe. Okay, and there was another problem that they were interested in, and it was the problem of in fact, they wanted to know what is the cheapest way to disrupt some of these roads to make sure that nothing can be actually shipped from Russia into Europe. Okay, so it was actually the main problem that they were looking for. And what was the cost if they actually disrupt a road? The cost of disrupting that road is the amount of the rate at which the material can be actually shipped. Okay, so this is the background about the network flow and the minimum cut maximum flow problem. So let me actually now introduce the formal problem. Given a directed graph with V vertices and E edges, and two nodes that we call them source and target, or instead of target you might actually see sink in different textbooks. The maximum flow problem is looking for the largest amount of material that can be transformed from the node source to the target. And the minimum cut problem asks for minimum damage that needs to be done to completely disconnect source from the target, that you cannot actually pass anything else from source to the target. Okay, so and here in this graph, the edges are showing the weight of the edges are showing the capacity. So let me actually just show you an example, so to make it less abstract and practically see that what would happen here. So assume I have a graph like this, and with these edges, and the source is this node S. The target is the node T, the target or the sink. And the capacity or weight of all of the edges has been actually specified on each edge. So here I am looking for minimum cut, but let me actually show you a couple of cuts and then tell you that we can have different cuts, and each cut is going to have its own cost, and among all of the possible cuts we are looking for the minimum cut. So I can define a cut as, for example, a cut is going to be, formally I can define a cut to be a partitioning of the nodes to two disjoint sets. We call it big S and big T, where the node, the source node, is supposed to be a part of one of these nodes, these sets, and the target should be in the other one. So it doesn't really matter how you, in fact, partition the nodes. The only constraint that we have here is that definitely source and target should not be in the same sets. So we usually actually say that source is supposed to be in S and target is supposed to be T. So one cut that I can consider is that only put the source in one set and the rest of the nodes put them in the big T. Okay, so here S is, little s is going to be S, and the rest of the nodes, all of them will be actually in T, right? This is one cut. It is possible that, I mean, depending on your graph, there are many different actually cuts that you can actually consider for each of these nodes. You should just put S in one and T in the other, and for the rest of the nodes there is going to be two options, and so almost 2 to the power of n minus 1 different partitions you can actually think of, something around that, or half of it in fact. Okay, so we define the cut. What is going to be the capacity of the cut? The capacity of the cut is going to be the summation of all the edges, the summation of the capacity of all the edges that are going out from the set source to the set target. So here it is going to be the summation of 10, 5, and 15. Okay, just the summation of outgoing edges from S to T. You can see that you can actually show it using this summation, all the capacity of all the edges that the edges UV, that U is a part of S and V is a part of T. Okay, so the capacity of this cut is going to be 30. Let me show you another cut. I told you we can actually have many different cuts. This is another cut that I put the first 4 nodes into S and the rest of the nodes is going to be in T. And so what is the capacity? Consider all the outgoing edges and add this, the capacity of all of them. So 9, 15, 8, and 30. And so the capacity is going to be 62. And you can see that there might be some incoming edges into S, and we don't actually consider them. The capacity of the cut is just the summation of all the edges which are going out from S to T. And so you can see that yes, the capacity of different cuts are going to be different. This one was 30, this one is 62, this one is another cut that you can see that if you add the summation of all of these outgoing edges here, 10, 8, and 10, it's going to be 28. So we have different cuts and we are looking for the cut with the minimum capacity. So this is going to be the problem of finding the minimum cut. I think now it is more sensible. It's actually just formally defined here that this is the minimum cut problem. So now let me actually just show you what is the maximum flow problem. We define a flow of the network to be some kind of assignment to all of the edges in the graph. That this assignment is in fact going to be the amount of flow that you assign to the network. So the original weight of each edge is going to be the maximum capacity. So it means that 10 means that it is possible to pass 10 I don't know, 10 different trucks through this road from S to 2, something like that. So it's just show you the maximum capacity, but you don't necessarily use the maximum capacity to send the stuffs. Okay, so the flow is some assignment to all the edges under two constraints. First of all, the assignment for each of actually these edges, if you are assigning some flow to the let me actually just use a different graph. If you are assigning some flow to each of these edges, the amount of flow that you assign to each edge should be at most equal to the capacity. You cannot pass more than capacity, of course. And the other constraint is that you should actually assume that in each of these edges, each of these nodes, that this is going to supposed to be corresponding to, I don't know, a city, a region, whatever, we don't have a storage to keep the material. Whatever you send to this node, you should actually send it out. So the summation of incoming flow and outgoing flow is supposed to be the same. So if you are sending, for example, 9 flow here, you should definitely send out all of that 9 out. So it's your decision that, for example, send 5 of it here and 4 of it here, or whatever our other distribution. Anyway, you should actually send out all of that 9 flow which is incoming to this node, and it is supposed to be valid for all of the nodes in the graph. So here you can see one flow defined over this network, and as you can see, I show the flow of all of these edges in blue on top of the capacity of each edge. So for example, in this edge we didn't actually send any material, so the flow is 0. In this edge we actually passed 4 material fully actually to the capacity of the flow. Or for example, sorry, let me, okay, and the rest of actually these flows. So you can see that this is a flow, and for a flow we define a value. What is the value of a flow? The value of the flow, in fact, is going to be the amount of material, or the summation of outgoing flow from the source, which is going to be equal to the value that the flow that you get at t. The point about the flow under this constraint is that you can make sure that whatever material that you sent out from the source, you definitely would get it at the target, because you didn't actually keep anything at any of these internal nodes. I forgot to actually mention that constraint about incoming and outgoing is just for the internal node, not about source and target, of course, because you send the material from the source and you are supposed to receive it at the target. Okay, so whatever material that you sent out from the source, you will receive it at the target if you assign a flow under that two constraint, that maximum. You actually just you don't violate the maximum capacity, and the incoming and outgoing summation of the flow should be the same for all the internal nodes. Okay, so in this case, you can see that the value of the flow is going to be 4. This you exactly sent 4 flow from source and you received 4 at the target. And we have different ways to assign flow to the edges, right? This is one way, this is another flow. You can see that I actually completely changed the capacity of many of these edges. For example, here we use the full capacity of this edge. We use 3 from this edge. We use 11 from this edge, and for all of the edges, um, we send some flow less than the capacity or equal to the capacity at most. And for all of the nodes, if you actually add, you can see that the incoming, which for example here is 8, is equal to the outgoing flow. Or for example here the incoming is 11, the outgoing is 1 here and 10 here, 11 again. So this is another flow. What is the value of this flow? The value of this flow is going to be the summation of material that you sent out from the source, which is going to be 24, and it is exactly equal to the amount that you receive at the target. Just like that problem of minimum cut, that you can have different cuts and you were looking for the minimum, here we can have different ways to assign the flow to the edges, right, under those constraints, and we are looking for the maximum flow. Here is another flow that you can see that, for example, this was the value of this flow was 4, the value of this flow was 24, and the value of this flow is 28 if you get the summation of all the values going out from S. Okay, this is going to be 28. So the maximum flow problem is that you are looking for the maximum, the flow that has the maximum value. So basically it tells you that what is going to be the maximum amount that you can ship from the source to the target using this graph with all these capacities that you have. Okay, so before I in fact go to the algorithm and tell you that how we can solve these two problems, I wanted to in fact discuss the relation between these two problems, which is very in fact interesting. Maximum flow and minimum cut problem on the same graph. So the very first actually observation that we have here is that if f is a flow over a graph, okay, and assume that I have a valid cut partitioning the graph into two sets S and T, the source set and the target set. So if I have a cut like S and T, over that, the flow that I have, I can actually show that the value that will be passed through the cut is going to be equal to the value of the flow. So consider this flow. It was one of the example flows that I showed you. This flow has the value of 24. Okay. So I wanted to actually tell you that it doesn't matter which cut you take. For all the valid cuts that you partition the source and target and all the nodes into two sets, S and T, that source is in one set and T is in the other, for any valid cut, the value that will be actually passed through the cut is going to be equal to the value of the flow. It's going to be equal to the amount that you actually are going to actually receive at the target. So let me actually just show you that I can actually consider different cuts, right? For example, this is one cut that you just put S in one set and the rest is going to be actually in T, right? So the value that will be passed through the cut, be careful, this is not the capacity of the cut. This is the value that will be passed through the cut. So here I just have outgoing edges. So it's going to be the summation of 10, 4, and 10. Okay, that's going to be 24, which is exactly equal to the value of the flow. If you consider another cut like this, the value that will be passed through the cut, so it's going to be the summation of 6 you will pass here, 0 you will pass through this edge, 8 you will pass through this edge, and you are actually sending them out, okay, and 10 you are actually passing out. You get the summation of all of this, and be careful. You should also consider this fact that it is not the capacity of the cut, it is telling you that how much amount will be actually passed through this cut. So not only you should consider the flow of all the outgoing edges, you should subtract the summation of all the flows which are incoming to S. So here I have an edge which is coming into S from T, and I should subtract the flow of this one from the summation of the outgoing flow. Here it is 0, and if you actually just add 6, 8, and 10 minus 0, that's going to be 24. Let me show you another cut. In this cut, I have these outgoing edges again. You get the summation of flow of all of these outgoing edges, which is going to be 10, 8, and 10, and you should subtract the flow which is incoming into S, and that's going to make it 24. Okay, exactly equal to the flow. So this is, it's a kind of actually observation. Then later on, I'm going to show you a couple of actually lemma, and at the end, all of these observations and lemmas are supposed to help us to understand the relation between what is the relation between the problem of maximum flow over a graph and minimum cut. I think you kind of have some sense that how they are going to be related by now. So, so far we have talked about the flow that is passing a cut. The flow that is passing the cut is going to be the summation of the outgoing flow from the source set minus the incoming flow from the target set. Okay, so the summation of all the flow of all outgoing minus the flow of all incoming. The summation of all incoming flows. The first lemma that I can simply prove is that, of course, if you have a flow over a graph and you actually consider any cut over this graph, the flow of the cut is going to be less than the capacity of the cut, right? Proof of this one is completely, it is going to be very easy. The fact is that the capacity of the cut is going to be just the summation of the outgoing edges, the capacity, not only just the summation of the capacity of all outgoing edges from the source S to the source set to the target set, right? And you are just adding all the capacity, and you don't actually consider the incoming of the edges. That's going to be definitely, so this is going to be just the summation of all the capacity of all the outgoing edges. Although the flow of a cut is going to be the summation of the flow over all the outgoing edges minus the flow of the incoming edges. So this part is going to be just bounded by this one. And you are, in fact, subtracting something from that as well. In the best case, this is supposed to be 0, and this one is definitely bounded by this capacity. So, of course, this is going to be very easy to prove that the flow of the cut is going to be less than or equal to the capacity of the cut. In the best case, the flow of the cut is going to be equal to the capacity of that cut. So, yes, was actually the lemma that we proved. And the second lemma that's going to actually help us to find the relation between minimum cut and maximum flow is that assume that I have a flow over the network. I have assignment of the flows over the network. In fact, it just tries to tell you that the flow of all the different cuts are going to be the same. Okay, so this part that is, this lemma that is written in this way is just telling you that if you have a cut, if you take one of the vertices from the target set and just put it in the source set, it's just telling you that you are changing the cut. Take one vertex from the target and put it in the source, or vice versa. Take a vertex from the source and put it on the target side. It doesn't really matter. It just basically tells you that for all the different actually cuts, the flow are the same. And we already actually saw this as an observation. Here it's actually just, we can know after that lemma 1, we can actually prove this one. And the proof is going to be very simple again. We can actually formally prove this one. The reason is that when you, for example, you consider this cut, if you, for example, take any of these nodes and assign it to the source side, the fact is that by assigning this node to the source side, how you are changing the flow of the cut, all the incoming, the weights that, the flow that is assigned for the incoming here are going to be actually moved from the target to the source side, and all the outgoing are going to be assigned to the target. So anyway, the flow is going to be exactly the same. So just moving one vertex from a source to the target is not going to change anything. And basically this lemma is exactly that observation that we already actually talked about. And this is telling you that how we can write the proof a little bit more formally. So now that we have these two lemmas, the fact we can see that it's just actually showing you different cuts over the same flow, and it's just showing you that if you are changing the nodes between the source and target sets, the cut is going to be the flow of the cut is going to be exactly the same. Okay. Okay, so from all of those, the first and second lemma, what we can actually just conclude here is that the value of the flow that we have, we already actually know that the flow of each cut is going to be bounded by the capacity of the cut, right? And we know that the flow of different actually cuts in the problem is going to be equal to the value of the flow. Okay, so it's just telling you that in fact because we can have different possible cuts, right? And those cuts are going to have different capacities. But the value of the flow of all the cuts, if consider that the flow is fixed, okay, but the cuts can be actually changed. So consider that I have a flow. So this flow, the value of the flow, is going to be bounded by the capacity of the cuts. You can have different cuts, remember? And we were looking in the minimum cut problem, we were looking for the minimum cut. So it is, now we can have this fact that it doesn't matter which cut you are actually taking, always the flow of this network is going to be bounded by that capacity. So in fact, the maximum value that the flow can get is going to be the minimum cut. In the best case, it can reach to the minimum cut because it's always bounded by the capacity of the cut. Okay, the minimum capacity of a cut. So this is exactly where these two problems are reaching to each other. On the same graph, the maximum flow is going to be at most equal to the minimum cut. And these two problems whenever you have actually in um, some kind of linear programming, if you have two problems related to actually the same structure, that in one of them you are looking for a minimum, the other one you are looking for the maximum, and the values of these two are actually bounded by each other. It means that the maximum actually value of the first problem is bounded by the minimum value of the second one. We say that they are the dual of each other. And so we can actually, in fact, at the end, write down a theorem like this, that maximum flow minimum cut theorem, that shows over any network, the maximum flow of the network is going to be equal to the minimum capacity of a cut in that network. So this is exactly that relation between these two problems, that the maximum flow over a network is going to be equal to the minimum cut that you can find in that graph. So the interesting thing about the problems that have this duality theorem about these two problems is that you can actually solve one of the problems, and in that way you can find a solution for the other problem. Both problems are definitely, you are defining them over the same graph, right? So okay, this was all about the duality actually of the maximum flow and minimum cut, and the rest of this lecture we will talk about the algorithm, how we can find the minimum flow. Okay, so then that's this part. I'm going to talk about it on the next part.